Okay, so new topic today. We're going to do some more multivariable derivatives. Actually, we're going to really kind of, today we're kind of, for the first time, going to really do a truly multivariable derivative. So what do I mean by that? Well, let me point out that the sort of multivariable derivatives we did last time were derivatives of parametric curves, and there are, in fact, multiple variables in that there are multiple output variables. But there was still only one input variable. I don't know if y'all thought about that, but a parametric curve, position is a function of one variable, time. Right? So in a certain sense of the word, and ultimately in the more meaningful sense, it wasn't really quite a multivariable derivative. So that's a little bit of a disappointment. But so today we're really going to do, no kidding, a multivariable derivative, and it's called a directional derivative. I want to flash y'all back before we get into this to single variable derivatives and remind you we have a point of view on what a single variable derivative is, and that is we're going to momentarily forget about slopes of tangent lines to graphs. Right, that's the sort of it works okay in a single variable calculus setting, but we need to deal with the possibility that we'll have too many variables running around. So our new point of view is that a derivative is a relationship between input changes and output changes. Or you have a domain, you have a target, and talking about if there's a change in the input, what's a corresponding change in the output? Okay, so we talked about that in the first section of this chapter. So this is really just a picture of that idea extended to a multivariable, a really multivariable function. You'll notice that there is a multivariable domain here. Two-dimensional as I have it drawn, could be higher, doesn't matter. And a multivariable target. And this relationship between input changes and output changes point of view fits fine with this multivariable picture. So in particular, if I'm at this point in the domain and if there's a corresponding output point there, I could talk about what would happen if this input point started moving with some velocity. This is an input change. This is a rate of change. This is what it means for things to move, right? In space, is they have some sort of a velocity. And to say what's the relationship between input changes and output changes would suggest that we should be interested in the resulting velocity of the output point. Right? So this is the point of view I want to take on derivatives, and ultimately this is the point of view that I want to be the sort of the fundamental point of view on what is a multivariable derivative in your mind. When you leave this course and you think of multivariable derivative, I want you to think about a relationship between input changes and output changes. And again, in a multivariable context, this is what that looks like. Okay. Now, question is, how do I then compute that vector? So we're going to see various different means of doing this throughout the course in different contexts. I want to start off with a fairly brute force construction, which is not the most efficient, ultimately, way to do this, but it has some really nice advantages that I'll talk about as we go through the course. So here's the idea. Keep in mind we're entertaining a situation where we have a point in the domain, corresponding output point in the target. I'm going to zoom in a notch here and give us some more room to work on this picture. There we go. So, right. So here's our situation. Again, we have a function that takes input points from the domain and gives us outputs in the target. So I would like to somehow conjure this scenario algebraically. Namely, I'm at this point and moving with that velocity. How do I write that down algebraically? And it's a pretty simple idea of how I'm going to do this. I'm going simply to create a parametric line that does as instructed. Namely, I'm going to create a parametric line that starts at that point and which moves with that velocity. And here's how you do it. That's the little formula that does it. And it's not a hard calculation to confirm. You take this formula for x of t. Now recall the construction here. This is a parametric line from Chapter 1. Okay. Where is this when t equals 0? Well, it's right there. It's at A. Plug in t equals 0, you get a, bam, just like we're supposed to be. What's the velocity of this parametric curve when we're at that point, as we are supposed to be? Well, the velocity we saw last time, this parametric line being as it is a parametric curve, the velocity is computed by the derivative. Let's take the derivative of this parametric curve with respect to t. The derivative is v. Right? So it's really a very simple little construction, but this perfectly algebraically conjures the idea that we're wanting to get across, namely that we're at this point moving with that velocity. So that's our sort of first step in the process. Now let me zoom out a notch and come back up here. Notice that this parametric line we just computed. Now, what do I want to do with that parametric line? Well, keep in mind the idea is that I'm trying to keep track of how this point is moving. Right, as I move along in the domain, these output points are going to be moving as well. Now, they're probably not going to be moving in a straight line, but they're going to be moving in some way. And in fact, they're going to create a parametric curve. We have position as a function of time going in. If I take these positions, plug them into f, I get other positions over here. So over here I have position in the target as a function of time. And so again, just another parametric curve. So the goal, keep in mind, was I want to know if I'm here and moving with that velocity, I want to know how fast, or said differently, what is the velocity of that output point. Okay, so the way we're going to get our hands on that is to observe that these points here, let's see, color choice, I'll do this in orange, that point there is f of x of t. So here's my position in the domain. Plugging it into the function, maybe I better be color consistent there. Here we go. Plugging these points, these domain points that are at a moving with velocity, plugging those into the function f gives me my position over here. And derivative is a way of saying what's the velocity of that image point. So the thing that I'm looking for, the velocity in the output, the velocity of the output given a certain given velocity of the input is simply the derivative of this parametric curve being f of that parametric curve being the one that's at point A with velocity B. So it's a very brute force construction. I just directly construct a scenario matching what I'm given. I plug that into the function, and I compute its velocity with the derivative. Okay. So this is what we're going to call that construction right there. This gives me that velocity vector. That's what we're going to call the directional derivative. Okay, now again, let me just remind you, our construction. There's my point in the domain. Here, let me zoom in on this. Focus on the algebra. There's highlighted in green there is my point in the domain. It's at the point A, moving with velocity v. F of that tells me what its image is moving around in the target. And then taking the derivative then gives me the velocity of that output point. So one way to say this then is that we start with an input velocity v, and the result is an output velocity. So this construction here, this directional derivative, the directional derivative is the output velocity given that you're moving in the domain with an input velocity. All right? How are we doing? Any questions? Does it seem like a natural thing to talk about. Again, a relationship between input velocities and output velocities. Everybody see the connection to single variable derivatives? Okay. All right. Right. So let me acknowledge a semantical awkwardness. This thing that I'm calling the directional derivative is not exactly the same as different uses of this term. So this is an awkwardness. In some contexts, the term directional derivative is reserved for when the input velocity, this input velocity here, is a unit vector. Now, there are a couple of good reasons to do this. We'll talk about those in the next section of this book. I have an entire section called Unit Directional Derivatives, right? And some nice things that happen. Unit directional derivatives are useful and valuable. But this more general construction is also useful and valuable. So I like to use this term in the more general sense. Directional derivative, as I define it here, this input velocity vector can be any vector. And we will worry later about how to reinterpret it if the input velocity is a unit vector. Okay. So that heads up outside of the context of this course. Anytime you hear someone use the term directional derivative, you need to be on the lookout for, wait a minute, in which sense do they mean? Do they mean in the direction of the vector that are they suggesting that I should infer the corresponding unit vector and that's what they meant, or do they just mean this construction that I'm doing here? In different contexts, it means different things to different people. So look for context clues, and if you can't be sure, I encourage you to ask to clarify. Okay. So let's talk about interpretations of the directional derivative a little bit. These are just restatements of things that we kind of already talked about. But we can do it anyway. So the directional derivative, the directional derivative is the rate of change of the output of the function, as I've indicated there. The rate of change of the output of the function. There's the notation for it. Given a certain rate of change of the input of the function. Right? So this construction says if you give me an input rate of change, an input velocity, the directional derivative computes for you the output velocity, the output rate of change. So that's one way you can think about the directional derivative construction, and that's the way I sort of presented it in the motivation that I gave. So here's a different interpretation, though, of the directional derivative. And so recall that when we were talking about single variable derivatives, you can think about single variable derivatives as a relationship between input velocities and output velocities. That's kind of what we did here. But you can also think about single variable derivatives as a relationship between input discrete changes and output discrete changes, or at least it's an approximation of a relationship between, delta x and delta f, delta x, delta y, depending on how you want to write things. So that works for directional derivatives as well. So directional derivative can be thought of as an approximation, to be fair, of the discrete change in the output given an input change v. Okay? So two different interpretations, and use whichever is useful, relevant to what you're doing, but both of these are reasonable interpretations of the directional derivative. Okay. Different contexts in which this might make sense. Let's look at this picture here. This is what the directional derivative construction looks like if you're talking about a real valued function. Now recall that when we wrote down the directional derivative, here was our sort of initial picture. And we were considering where not only are there multiple input variables, but there were multiple output variables. And so we interpreted the directional derivative as a vector in the target space. And that's true here as well. It's just that you might not think of it as a vector in the target space if the target is R1, right? So this is what we call a real valued function because the values of the function are just real numbers, one at a time, a single real number. Okay? So in this context, the directional derivative is, you might just want to think of it as a rate. You don't need to really think of it as having a direction. It's real value. There's really only one direction. And so, for example, this might be different things you might interpret. This might be the temperature function, in which case, when you're at that point and moving with a certain velocity, this just says, how fast is the temperature increasing? It's a rate. It's degrees per second. Degrees per minute, whatever your units are. Okay. Another context in which this might make sense is what if you have a single input variable and multiple output variables? Okay, well, in this case, it looks an awful lot like a parametric curve, doesn't it? And the directional derivative, well, wait a second, we already have a sense of a derivative of a parametric curve. Derivative of a parametric curve is the velocity vector of that parametric curve. And not surprisingly, there's a strong relationship here as well. The directional derivative can be related to this plain old, good old velocity vector of that parametric curve. And there's one little twist on here, and that is that when we're talking about the derivative of a parametric curve, we assume, since this is the t-axis, and we're taking the derivative of the parametric curve with respect to t, the assumption is that the input velocity, and what's the rate of change of t with respect to t? Well, it's 1. Okay? So if you want to make this interpretation of the directional derivative as being a velocity vector for a parametric curve, the only hitch is that you have to be sure to interpret this velocity vector as 1. All right. Okay, so let's do an example. Here's a function. 3 inputs, 1 output. So this is one of these real valued examples. And so keep in mind, when we say that we're going to compute the directional derivative, we're computing just a rate of change. Again, you can think of it as a velocity vector, but you don't have to. You could think of it as just, maybe this is the formula for, again, temperature is a function of position, or what have you. I just want to know how fast it's changing. I'm going to assume I'm moving with a certain velocity in the domain, and I want to know how fast is this single value changing per unit time. So let's compute that. Specifically, I'm going to assume that I'm starting at that particular point and moving with that velocity. So this is sort of the given information in the input. I'm there and moving with that velocity. And it's with that understanding of being at that point, moving with that velocity, that I want to know in the output how fast is the function changing. So I'm computing the, wrong picture. Computing how fast is the function changing given that I'm at a given point and moving with a given velocity. Okay. So let's do it. Let's turn the crank on this. This is a very plug-and-chug calculation. You'll notice that the very first thing that I do is observe that the rate that I am looking for is, in fact, just the very motivational definition of the directional derivative. Directional derivative says how fast is the output changing, given certain information about the input. Again, given that we're starting at that point A and moving with that velocity V. And then notice further, the very next thing I do is just write down the brute force definition of the directional derivative. In other words, I'm going to construct the parametric curve that does what I'm told to do. I'm going to plug that into the function, and then I'm going to see what's the rate of change of that as time passes. Okay, so here we go. Let's do the algebra here. Zoom in a notch. There we go. Okay, so we start off at that point, A, moving with velocity, V. Right, so here is my position as a function of time in the domain. Which, by the way, I can rewrite like that. And all I've done there is combine this linear combination of vectors into a single vector. Now, having done that, what do I do with this expression? Well, my goal at this next stage is to compute f of that input parametric curve. So I've got x, y, and z, and I need to plug those into our function. Now, quick reminder, our function is x squared plus yz. Okay, so you got to keep that in mind, x squared plus yz, and what this says is take this x, that y, and that z, and plug them into that function. So here it is, x squared plus y z. Brute force, right? Plugging straight into the definition of the function. So that's that. How are we doing? Everybody good? Right, so then, you multiply the whole thing out. This multiplies out, collects terms, you get that. And keep in mind, the way we compute how fast the function's changing is we just take literally the derivative of those values of the function. So here are those values of the function, and let's take the derivative, and, well, it's good old single variable derivative. That's an easy little calculation. And the very, very last thing, if we want to keep in mind, I'm interested in knowing what the value of this derivative is at a particular moment. It's when t is equal to 0. And let me remind y'all why that is. Here's our picture. And we've got this parametric line, but that parametric line is at the point I want it to be. I mean, this is where I want to know, what's happening with the function. The parametric line is at that point, only at the moment when t is equal to 0. Right? So I'm not really interested in this expression, really. Right? It's what that is when t is equal to 0. That's what I want to know. And that directional derivative in this case is 10. Everybody see how this calculation works? Any questions? Just plug and chug, yeah.
Would there ever be any circumstances where you would evaluate that with t equal to something else?
You could manufacture such an example, but there's never any real point to doing it, right? In some sense, if you're looking at this picture, what we know is we want to be here and moving with that velocity. Now you can create that scenario in a variety of different ways. You could parameterize this line starting at that point, and then moving with somebody, and then you'd be here when t equals 5. It's just it doesn't bias anything, right? So the inner lazy mathematician in all of us should motivate us to always just go ahead and start at A and then t equals A. It's easy to remember and it's easier to write down. Yeah. Does that make sense to everybody? It's a great question. Yeah. Okay. Right. Okay, let's see another example. Now this one's a little different. Notice here, not a real valued function. Right? This is a function whose values are vectors. So when we compute the directional derivative is going to be the punchline on this question. When we compute it, keep in mind, I'm not going to be getting a rate. I'm not going to be getting just how fast is a certain number changing, because the function I'm interested in is not a number. It doesn't have number values. It has vector values. So here, I'm going to be viewing these values as points in R2, and I'm going to be interested in in what sense are these output points changing? Specifically, what's the velocity of the point moving around there in R2? So the directional derivative of this vector valued function will be a velocity. Direction being critical to that. All right, so that being said, here's our scenario in the domain. We've got a starting point. We're moving with a certain velocity in the domain, and we want to know in the target, where that's the formula for the value of the function, I want to know what's the velocity of that output in the target. And of course, that's exactly what the directional derivative is. And the derivative computes, it's constructed explicitly to compute the velocity of the output in the target. Okay. Right, so again, we compute directly from the definition. There's a definition. Here we go. AV. So as before, I just plug in directly to the definition. This constructs my parametric curve in the domain. I then have to plug that into the function. Plugging this into the function, don't forget that there's your x, there's your y, and there's your z. Let's go back up and remind ourselves, what is this function? The function is xy, comma, yz. Again, it's not a real valued function. We have a vector valued function, so I have to remember the formulas for each component. First component is xy, second component is yz. And that's exactly what we do down here. Oh, oops, gosh, I didn't mean to do that. Exactly what we do down here. X, Y is the first component, and the second component is Y, Z. All right, so the same idea as we did in the last example. It's just that now this is vector value, so the values of the function that we get out are a vector. Then we're going to be taking the derivative of that vector. Now, there's a certain amount of algebra to multiply out, collect terms, etc. here. That's all that's happened there. And then here, I'm just taking the derivative. The derivative of that is that, and the derivative of that is that. Single variable calculus. Again, this is not exactly quite what we want. This tells me the velocity vector of the sort of the whole parametric curve for all values of t as this floats around and it goes to a bunch of points we're not interested in. This is only what I want at that moment when t is equal to 0. But I do have to, at the very end, plug in t equals 0, and that gives me that. Everybody happy? Yeah.
So, once again, going back to, like, if you were to plug in t equals 5 and say, oh, I'm looking at a point further along in the domain, then wouldn't you have to assume that the velocity in the domain is constant to be able to draw conclusions about what, like, the image is doing using that same velocity vector? So
if you were to plug in something other than t equals 0, keep in mind, our goal is we're given this point and that velocity, and I want to know what's happening over here. Right? If you plug in a different value of t at the end, if you plug in t equals 2, then that's going to say at this point, at which point you're sort of over here in the output, that'll give you that vector. And it's just not what we're interested in. Or I just crossed out the wrong thing. It's not what we're interested in. This is what we wanted, and I don't know why we're over here. You see what I'm saying?
Yeah.
I'm not sure if I answered your question.
I think basically I was saying, like, if you tried to use that same, like, 4t plus 5, 6t plus 6, if you wanted to say, all right, well, now let's look further along, and then it would work because you have, but, like,
I mean, look, if you do that, it does compute a thing, right? If you plug in t equals 2, I'm going to say, just because it's easier to draw, that would tell you that if you're at that point and moving with, in fact, notice that exact same velocity, then it would compute for you that resulting velocity in the output. It's just that, can't emphasize enough, this is what we're interested in, and that's a different thing.
Okay.
Yeah. So does that make sense?
Yeah.
So it's not that what you're describing is meaningless. It's just that it's not what we're interested in.
Right.
Yeah.
Okay.
Yeah. All right. Okay. So let's see. Maybe I better zoom out. Okay. right. Okay, so we finished this example. There's another example here. I'm going to let y'all read this one. It's not that different from the ones that we've just gotten through doing. I constructed a scenario where there's a bird that's going along flying in a certain way, and I want to know how is... let's see, what is this? Oh, yeah, the motion of his shadow. It's really just kind of a manufactured real-world example that relates to what we've already talked about. Okay, so I'm going to let y'all read that example on your own. The last thing I want to talk about is this component-wise computation. Y'all might recall we had some good news with parametric derivatives. Right? You have a parametric curve. You want to take the derivative of a parametric curve. We wrote down a formula because it was notationally familiar, which is not a good motivation, right? And we found that, not only does it have good geometric features, which is great, it's also really easy to compute. That was a lucky break, that parametric derivatives are computed component-wise. You don't have to reinvent a whole bunch of new shortcut rules. So, question, am I going to have to go through this process every time that I do one of these? In other words, do I have to do vector calculations every time? And in fact, the answer is no. And here's the reason why. The key point here is that that's a parametric curve. Right? Our velocity vector in the target, our motion in the target is a parametric curve. We already know that parametric curves, their derivatives are computed component-wise. So this directional derivative I'm looking at is a derivative of a parametric curve. So it's computed component-wise as well. So the observation that I've made down here is just that if it should be that you find yourself looking at a vector-valued function, like the last example that we did, we had a vector-valued function. You could do the derivative like I did, or you could one at a time, instead of computing that all at once, you could one at a time compute the individual derivatives of the component functions. These are then real valued functions and compute their derivatives individually. So one thing you might want to do, I'm going to encourage you to take this as a little exercise. Look back at this example here, where I computed the directional derivative of this function, right? And instead, compute the directional derivative of just xy by itself. Then compute the directional derivative of just yz by itself. And here's what you're going to get. For xy, you're going to get 5. And for the yz, you're going to get 6. Right? So I did them all at once here, and the argument could be made that maybe this is really actually kind of more convenient anyway. You're getting it all done all at one time. But if you want to, for whatever reason, you can do it one component at a time. Okay. All right, so I'm going to move on to the next section now and talk about unit directional derivatives. Again, this is there's a different point of view on what the word directional derivative ought to mean. And in different contexts, it's used. The term directional derivative is used in different ways. So again, be on the lookout. Be careful. Starting off, here's a reasonable motivation for why maybe our velocity should have to be a unit vector. Let's look at the term itself, directional derivative. Directional derivative says right there, direction. Right? How do we represent directions? Vectors not really quite representing just directions. Vectors are representing directions and magnitudes. Right? There's an argument that says if you want to isolate just a direction, you pick a canonically nice vector that points in that direction, and you try to have magnitude mean as little as possible, and the unit vector pointing in that direction is a pretty natural choice. So there's a point of view there. There's a semantical argument, but anyway. So I'm going to segue into what we can do with unit directional derivatives with a calculation here, the punchline of which is a neat fact. I'm going to talk about this fact first before I do the calculation. This is a little bit of a surprise, really. What this says is that if you have a vector, if you multiply it by a scalar, k, and if you ask, what's the directional derivative where you're moving with velocity not v, if you're moving with a velocity that is kv, in other words, if you scale your input velocity. Question, what happens to the output velocity? And the weird thing is that the output velocity that you had originally simply gets scaled by that same k. Well, it's not immediately obvious this is true. It's pretty satisfying if you kind of think about it. And let me go down now to this picture before I do the, whoa, too big, before we do the algebra. One way to say this is suppose you're moving with a certain input velocity and there's a corresponding then output velocity. What would happen if you moved 3 times as fast in the input? Well, you're moving along the same parametric line, therefore you'd be looking at the same output values. It's just that if you're moving 3 times as fast along those input values, you'd be moving 3 times as fast along those output values, and you would kind of expect with 3 times the input velocity to get 3 times the output velocity. It's a fairly physically plausible claim. All right. So that being said, let me prove this algebraically. I think it's a nice proof. I'm going to compute that directional derivative, again, where the input velocity is scaled. So this is the kv directional derivative. I compute that. Here's the definition of it. Notice that input velocity vector kv is what we're using as our velocity. Otherwise, this is straight up, right down the pipe, the definition of the directional derivative. And now I want to interpret what does this expression mean. I'm going to reinterpret this. Instead of this being my parameter and this being my velocity, I'm just going to move parentheses around just a little bit. And let's have that. Oh, I didn't do that right. Let's have that. I'm going to call S be my scalar, my parameter. And I'm going to have now just V be my velocity. So having just V being the velocity, notice, and with TK being redefined as S, notice I can rewrite this expression as that. Does everybody see what happened here? This is a little mathematical sleight of hand, sort of renaming, moving things around. Nothing really happened here. All right. So that being said, what is this expression? Well, I claim what we have here is a chain rule problem. This is a chain rule problem because I have a function of S, and I'm taking the derivative with respect to t. So think back to single variable calculus. How do you take a derivative? You have a function of one variable, you're taking a derivative with respect to a different variable. Well, the way you do that is you first take the derivative with respect to S, and then you multiply by ds dt. Right? So df dt, all that's happened in this step here is I've rewritten df dt as df ds times ds dt. Cool? Okay. All right. And having done that, let me observe that this is precisely the definition of that directional derivative. Specifically, there's my velocity vector. There's my starting point. And the only thing that's not, in fact, just character for character straight out of our actual definition of the directional derivative is that I'm using a different parameter. I'm using S to parameterize the line in the domain. Previously we used T. doesn't really matter, right? It's just a dummy variable that helps us parameterize a line. It remains, though, that here, this is a parametric line. I'm taking the derivative of that as the parameter moves, and this is still a relationship between input changes and output changes. Okay. All right. What is ds dt? That's k. Everybody good? So this proves our result. Specifically, our goal was to show, effectively, our goal was to show that scalar k can factor out, and that's exactly what we've shown. That scalar k factors out. Okay. All right. Nice fact, by the way. So, arguably, this is, in some situations, this is really a more useful and a more general fact than what we're going to do with it first, which is to use this as a way of defining a unit directional derivative. So let me do that latter thing first, but just don't forget this fact. Scalars move in and out of velocity vectors and directional derivatives in a very nice way. Okay. All right, so the situation I want to apply this to is, suppose we have a velocity vector v. Keep in mind velocity vectors. You can sort of think of a velocity vector as being made up of two sort of pieces. There's a direction and a magnitude. Right? So I'm going to say, suppose that our direction, is a unit vector u. Then the magnitude, of course, is just the speed. Now, beware of a notational pitfall. It looks like this says v equals vu. I guess it kind of does. But the first v is a vector. This v vector is both a direction and a magnitude. Right? This second v is just a scalar representing just the magnitude, namely the speed related to that vector. Not putting a vector hat over this one. So that being done, notice that I can use this fact to take, I can take this scalar and factor it out. Right, so the velocity vector v, this scalar speed, little v scalar, just factors right out of that directional derivative. Now, having done that, okay, fine. So what? What is it? How does this amount to anything? Who cares? Where's the benefit? Well, let's not forget what speed is. Speed is the magnitude of your velocity vector. It's the magnitude of the derivative of that input point, right? That input parametric line. Don't forget what the directional derivative is. The directional derivative computes the rate of change of the output. So what we find here, and this is a neat conclusion, is that in this situation where your input velocity is a unit vector, so this is our unit directional derivative. This blue highlighted object here, it's a directional derivative, sure, but where the input vector is a unit vector. Neat fact, you can interpret this as a relationship, as a factor, in fact, between input speed and output velocity. That's kind of a neat fact. We lost in the shuffle when we were talking about directional derivatives that in single variable calculus, we thought of the derivative as a factor. And we talked about how it's a relationship between input velocities and output velocities, but specifically the derivative is a factor. It's what you multiply by input velocity to get output velocity. That wasn't really true with directional derivatives, right? I mean, directional derivatives are not really multiplying anything. I mean, this is just a formula. If you give me an input velocity, then this is a formula that computes the output velocity, but by way of a weird construction. Right? Here, I've recovered the factor concept. And this is a nice fact, the unit directional derivative is a factor that you multiply by input speed to get output velocity. The factor that relates input changes to output changes. Okay, so that's one of the nice things about the unit directional derivative, and I've written that down here as in the interpretations, our initial interpretations of the unit directional derivative. It's a factor. And it's what you multiply by the speed of the input to get the velocity of the output. Cool. Another interpretation, I'll come back to that picture in a second. The unit directional derivative, what did I use here? Okay, right. The unit directional derivative is the factor that you multiply by some sort of a discrete change in the input, specifically the magnitude, the distance of that discrete change, to get an approximation, to be fair, of the output. So when you use a directional derivative and a unit directional derivative in similar ways, they're both things that you use to relate input changes to output changes. It's just in the directional derivative itself, the directional derivative is the output change. The unit directional derivative is a factor that relates the input change and the output change. All right, and it all comes out of this scaling business, where you can take magnitudes and scale them out like so. All right. Now, I'm going to show you some examples in a few minutes as to how to choose. You know, in which situation should I use a directional derivative or should I use a unit directional derivative? Which one? Which context? A couple things to be aware of there. One is you have to be clear in your mind, first of all, which one are you actually trying to compute? Sometimes you want one, sometimes you want the other, and we'll see some examples of those. Also, keep in mind, very largely, very often, the choice breaks down to which one's more convenient to compute. Right? And sometimes one is conspicuously more convenient than the other, and I'll show you a couple of examples. We'll get to that in a few minutes. But I do want to give you one last interpretation first of what a unit directional derivative is, and it comes from this picture. Actually, let me scroll up for a second. Come up to here. And remember, we just agreed that the unit directional derivative is a relationship between this. Now, what is this guy? This says the magnitude of the displacement in the domain. So that's a distance. That's a distance that you move in a given unit vector direction, u, sure. But this is a distance in the domain. And if we're talking about a real valued function, that is a distance, namely how much does the function increase? Just a change, scalar value change in the function. So now let's interpret that in this picture. Again, if we're thinking about a real valued function, right? Colors. Let's see, yellow and purple. Okay, right. So the unit directional derivative tells me, well, if I move a certain distance, yeah, in the direction, a given direction of a given unit vector, that's sure, right, fine. Then we can talk about how much the function increases. There's a distance that the function goes up when you move that certain distance. So altogether, what you get is that the unit directional derivative is the factor that you multiply by the yellow distance displacement to get the purple sort of change in the function displacement. Said differently, it's the ratio of purple divided by yellow. So the unit directional derivative, if you think about it, is a slope. And in general, the plain old directional derivative, the general directional derivative, doesn't have this feature. it's only the unit directional derivative, understood then as a relationship between distance changed in the input and the corresponding change in the output, that you can then interpret as sort of a rise over a run kind of a situation, and therefore as a slope. So you get this punchline, and that is that unit directional derivatives compute slopes of tangent lines. Now, specifically slopes of tangent lines to graphs, of course. Notice that here we're using height to represent the value of the function. So here we have z is f of x comma y. Right, so critically then this is a graph of that, sorry, I hit the wrong color, of this function whose directional derivative I'm computing. So very important fact, you have to keep this in mind. Keep in mind, whenever you're making geometric interpretation of multivariable functions, you've got to be critically clear in your mind which geometric picture are we looking at. Here, we're looking at the graph of the function whose directional derivative we're computing. Okay. And in that context, what we just showed is that given a unit vector direction, I guess I'll leave that there. Given a unit vector direction, as you move in that direction, if you were to look at a cross-section, vertical cross-section of the curve, as you're moving in that direction, that cross-section might look like, oh gosh, color choice. Cross-section might look like this. The unit directional derivative colors. The unit directional derivative computes the slope of that tangent line. Anybody see what we're talking about here? Nice fact. Okay. All right. So there's some examples here. Let me before I go on to those examples, I want to come back to this picture and talk about again the trade-offs of what should I compute in which situation, and or at least what are my options. Okay, so let's look at here's our situation. Suppose that what I'm interested in is computing the output velocity. Right, so I'm at a certain given input point. I'm here, I'm moving with some velocity in the domain, and I want to know what's the velocity of the target. Well, the directional derivative is exactly what does that. Notice that written down here, df dt, how fast the function's changing, directional derivative. Right. The alternative that you could do, what the unit directional derivative offers, is that instead, if you would prefer, for whatever reason, you could say, the thing about it is, something kind of inconvenient about that vector. Things would be easier if I entertained this vector. Well, let's consider what happens if I'm at this point moving with that unit vector velocity, in which case, well, I can compute under that scenario how fast would the function be changed. What's the velocity of the output? And that is this unit directional derivative. Now, is this the answer I'm looking for? No. Again, the whole point is I was interested in, given that input velocity, I want to know the corresponding output velocity. And I haven't computed that. I've scaled down the input velocity vector, and correspondingly, a scaled down output velocity. So the way you would use altogether the unit directional derivative to compute what you want is you take your input velocity, you divide by the magnitude to get a unit vector. You use that unit vector to compute your unit directional derivative, and then you multiply back by that same magnitude to get the object you're actually interested in. So, is that useful? Does it help us? Sometimes it does. And so let me show you an example of why it can be handy. This is just, there's lots of different situations where it might be useful. Okay. So here's kind of a little silly little real world scenario. Our friend Bob is walking around in the forest, and there's mosquitoes everywhere, right? That's annoying. Specifically, there is there's a pond somewhere, and those mosquitoes are breeding, in the pond, as they will do. And here's a function that tells us mosquito concentration as a function of position. So there's a pond at the origin, and then there's this sort of decaying, there's a lot of mosquitoes around, and there's a few nearby, and there's not as many that are further away. All right, so the question says, if Bob is here and moving with that velocity, how fast is this function changing? Now, at a glance, we have an input point and an input velocity. I know exactly what's happening in the domain. The question is, how fast is the function changing? At a glance, what we're looking for here is the directional derivative. So what does this have to do with unit directional derivatives? Why would I bother with unit directional derivatives? I'm going to do this question with unit directional derivatives and then talk about how nice this move was at the end. Specifically, the unit vector, he's moving due west. Due west is described by that unit vector. Negative 1, 0 points to the left on the map. That's west. So that unit vector goes there. His speed is 3.5 miles per hour, so that's the speed that I put in there. And I plug and chug. Now, how is this helpful? This was helpful because look at the parametric line. Look at that parametric line. X is 2 minus t, y is 1. Integer coefficients, kind of nice. Why are there integer coefficients here? Well, because where this came from was, this came from the starting point 2, 1 plus t times, now my unit vector velocity, negative 1, 0. It's because we scaled out and looked only at the unit vector that this is a nice vector. Otherwise, there'd be a 3.5 in here, which means inside your parametric curve you'd have a 3.5. By the way, it could be worse. What if instead of 3.5, what it was 3.48219? Well, now then you're going to be carrying 41829 or something all the way through your calculation. Right? The easier thing to do in this situation is realize that as far as the directional derivative computation goes, really it's the direction that is the most important part in most of this calculation. And the fact that it's 3.5 miles an hour, whatever, deal with that at the end, right? So you get a much nicer calculation here by scaling out the speed and using a unit vector. Everybody see how that works? By the way, you might amuse yourself just to get a up close and personal idea of what the alternative would have been. Is do this by computing the directional derivative directly, directly from the definition. Use a weird speed instead of 3.5 miles an hour. Let's suppose it was, make up some annoying, inconvenient number, and then do the calc and see if you see what I'm talking about. Okay. All right. Here's another example. This is a different example. So here we have a hill. An ant is walking around on a hill, and specifically the hill is the graph of a certain function. Now, recall that if you have a function of two variables, such as this one, if you look at the graph of that function, the graph then is it's a surface in R3, and I'm saying in this case it gives us a certain kind of a little hill, and that hill, an ant is walking around on the hill. Okay. All right. So interpreting this hill again as the graph of a function, I'm going to say that the ant is starting on the graph above that point, and he's moving in the domain in the direction given by that vector. He's not moving with that velocity. He's moving in the direction of that vector. And I want to know, what's the slope of his path? Now, notice, the question did not ask what is the rate of change of his height. You know, how fast is his altitude changing? Is he going to be getting altitude sickness? Nothing like that. It just says slope. So another way to say this is we're looking for not rate of change of altitude with respect to time. We're looking for rate of change of altitude with respect to distance. We don't actually know how fast this ant is walking at all. So just want to know the slope of that of the path that he's walking along. Okay. Well, thankfully, slopes are unit directional derivatives. Right. And so in this case, what I'm looking for is the unit directional derivative. I'm actually not interested in the directional derivative at all. This kind of thing will come up sometimes, where the question at hand, unit directional derivative is not just a tool that may or may not be useful to compute directional derivatives. Sometimes the unit directional derivative is what you want. So one of your jobs as students in this course is to diagnose. I mean, look at the problem, see how it's phrased, see what the question's actually asking for, and then make the right decision as to, wait a minute, which of these two things should I be computing? Okay. All right, so I need to compute a certain unit directional derivative. I'm talking about that which points in the direction of the vector 1, 1. And here's how you do that. I found the unit vector here that points in the direction of the vector 1, 1. So now what you could do, if you were so inclined, you could brute force this problem and compute unit directional derivative. There's your unit vector. And off you go. And that would be fine. Except it would also be annoying because, again, non-integers. Right? This vector is there's a fraction, there's a denominator of the square root of 2 that would move its way all the way through this calculation. So what I'm going to do in this example, just again to show you the flexibilities and choices that you have, is sort of scale out, not the magnitude of v, but I'm going to scale out 1 over the magnitude of v. Said differently, I'm going to compute the directional derivative, the unit directional derivative that I want by scaling out that scalar, right, and computing with just 1, 1 as my velocity vector. Now, I emphasize, it's not because I actually want this dvf. I'm not actually interested in that directional derivative. It's just that this is easier to compute. Again, look at the nice integer coefficients in this whole calculation, very convenient. This is easier to compute with, and I can relate it to the thing I'm actually interested in, namely the unit direction. So kind of a double twist in some sense in this example. It's we use the scalar factoring, and we use the sort of new idea that we might be interested in something other than the directional derivative. Okay, one last example. Yeah, one last example. So suppose I've got some function and I want to compute the directional derivative. So I want to know how fast this function f is changing with respect to time. Again, keep in mind that's what the directional derivative computes is df dt, right? And suppose my input velocity is the vector 2, 7, and what do we do? How can we compute this? I would like to point out that this is a situation where the unit directional derivative offers basically nothing. Right? So why would I not just compute this directly? The vector, fine. Integer coefficients. Integer coordinates, that will give me then integer coefficients when I do the calculation. the alternative, I suppose, it'd be weird. I suppose I could take this vector, determine its magnitude, which is the square root of 53, right? And then I could divide by the square root of 53, compute the unit directional derivative, carrying that square root of 53 through the whole calculation, which would be super tedious. And then at the end, acknowledging that that computed the unit directional derivative is not what I wanted, and then multiply the result by the square root of 53. Why would I do that? Right? There's a bunch of extra work involving the square root of 53 that gets you to the exact same answer that we would have gotten had we avoided all that extra work. So the reason I put this example in here is I don't want students to think that somehow it's like morally better to use the unit directional derivative than the directional derivative. It's not. I'm not trying to encourage you to always do this. I want you to do this if it's convenient. Right? In this case, it was convenient. I got to get this annoying scalar 3.5 out of the detailed algebra of the calculation, and life is just a little bit easier this way. So if it's convenient for your purposes, yeah, absolutely. Right? Or if the unit directional derivative is what you actually want in the first place. Yeah, for sure. But don't just do it reflexively in a case like this. Everybody happy? Okay. Final reminder, make sure to remember that there are these different interpretations, different contexts. Some people, when they say the word directional derivative, what they mean is unit directional derivative. There are many textbooks where the word directional derivative is defined as a certain formula, not unlike what I wrote down, with the understanding that that has to be a unit vector. Right? So outside of this particular offering of Math 212, in your future applications of multivariable calculus, you might hear someone talk about a directional derivative, and they'll give you a vector, and they might not clarify. And you have to make sure to realize this is one of these unfortunate confusions of terminology. It's not consistent. Make sure to clarify. Look for context clues, I suppose. Right? And if there's context clues, great. But beware of the possibility you might have to ask for clarification. Wait a minute, what do you mean in this case? Yeah?
Would they call the non-unit version of the directional derivative something else? Like, is there another name?
I have not seen one. I guess there's an answer I could give after a few more lectures forward. We'll see a new fact called the chain rule, multivariable chain rule. Some people might say, this is just a multivariable chain rule computation. I'll make sense out of that in the context when we get to there, but not really. Yeah. All right. Okay. Next kind of derivative we're going to talk about. This is a further special case of the directional derivative. So let me remind you, the very first thing we talked about today was the full, most general directional derivative. We've got some input point and any velocity vector that I might be moving, that might be describing my motion from that point. Any vector. We then considered a special case of that construction. The special case is the unit directional derivative, which says, no, you can't just move with any. We're going to reserve the term unit directional derivative to where in the domain, when you're at a certain point, you're moving with a unit vector velocity. And certain kind of nice things happen. For one thing, we get a connection to slopes. For another thing, we get to reinterpret this unit directional derivative as a factor, which smacks of our interpretation of the single variable derivative. So that's nice. Okay, this is a further special case. This is a special case of that special case. So now, not only are we going to require that we're looking at a unit vector, but we're further going to require that that unit vector be not just any unit vector, but that it must be a standard basis vector. Okay, it turns out that something really nice happens. So here's how that works out. Let's consider here we go. We're computing directional derivative. That vector is not just any vector, it's a unit vector, but in fact it's not just any unit vector, that's a standard basis vector. So how does this calculation turn out? Well, here's the definition of directional derivative. Now I want to write down the definition of that single variable derivative. How do you take the derivative of something with respect to s? So flashback to Math 111L, that single variable derivative is this limit. All right, now I'm going to leave this as an exercise for you guys to sort of think through, wait a second, what is the definition of a single variable derivative? Right? And in this situation, how does that give us this? It'd be a great little practice problem. Right? Think it through. It's not quite immediately on. You've got to write down the definition of a single variable derivative, apply it to this circumstance. This is what you get. Okay. Alrighty. So now I'm going to expand out the various items in this expression here. They turn into this. Specifically, note that our input point A there is actually a vector, and our direction is a standard basis vector, so that's got various components there. And now here's that A point again. That's the same A. So altogether, I haven't really done anything. I've just sort of expanded out what this is, where I can see the input components more conveniently. Fine. So what? What's interesting about this is this allows us to observe that the first component here doesn't change. That first component is A1. We're taking f of this minus f of that. The first component is A1 here, and it's A1 there, because that is a 0. Okay. So said differently, the first variable, for the purposes of doing this calculation, here, where we have a unit, not only a unit vector, but a standard basis vector, the first variable is constant throughout the entire process. As h approaches 0, as blah, 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 that first variable is not changing at all. It is behaving as a constant. Likewise, for most of the rest of these, you'll notice. Right? They're not changing. They're just constant because I keep adding zeros to them. All of those numbers are 0. All of those numbers are 0. And so all of these numbers, all constants. So the only thing that's not constant is this variable. Right? It's A1 there, and it's A1. AI is sort of the starting value, and it's AI plus H over here. So that's the variable that's actually changing. As we're taking a limit, as we're computing this limit that is the definition of a derivative, only that slot, only that input variable is actually changing at all. Okay. Now, the upshot of this is really, really nice. The upshot is that if I want to compute this directional derivative, unit directional derivative. There's a further special case where this, again, is a standard basis vector. In that very special case where that's a standard basis vector, I can treat all of the variables except for one as if they are constants. Because they are. Right? For the purposes of computing this directional derivative, all the variables except for one are constants. And what's left over, viewing those many other variables as constants, notice that what's left over is a plain old single variable Math 111L derivative. Namely, ignore all the constants. These are just the green here, just constants, whatever. We have f of that one variable minus f of, well, in that same variable, and it's a plus h. Here it's an a, you subtract, you divide by h. It's a plain old single variable derivative, where we take the multivariable function and interpret all of the other variables as being constants. So here's how this works out. Suppose that this is the function I want to compute that directional derivative of. And suppose that I'm going in the direction of the E1 vector. Well, E1 points in the direction of x. So effectively, because I'm going in the E1 direction, effectively I'm just taking the good old, plain old single variable derivative with respect to x. And I'm going to treat y like a constant, because again, it is a constant as far as this derivative is concerned. So this calculation works out really conveniently. That's a function I have to actually take a derivative of, and that's a constant, and that's a constant, and so look how easy the derivatives are. The derivative of x squared times a constant is 2x times that same constant. Derivative of y squared, let's see, y is a constant, so y squared is a constant, and its derivative is 0. Super convenient, right? Okay. So they call this a partial derivative, and I just looked at the clock and realized that I've gone over time. So this is a pretty good stopping point. We'll end there and pick up here next time. See y'all later.